Good day, class. So for this particular set of slides, this will be your continuation for unsteady state and convective mass transfer. And for this one, I'll be discussing convective mass transfer coefficients. So our convective mass transfer coefficients may take several forms, which I'll be showing to you later on. And these particular forms are actually interconnected with one another through, of course, a set of formulas. Now, real convective mass transfer has to be understood when and does it happen, and what is its difference between the usual discussion that we have regarding mass transfer or the things that we have discussed previously regarding mass transfer. So in our previous discussion, the mass transfer phenomena is viewed as a simple molecular diffusion. Molecular diffusion in the sense that the flow is laminar. Now let's going to look into a particular circumstance or what brings about this particular convective mass transfer. That way, you'll be able to understand the formula, understand the principle behind the formula that we're going to use. That way we can determine what a particular problem requires from us. Now, to have a fluid in convective flow, it requires that that particular fluid has to be flowing past another immiscible fluid or a solid surface. So we have convective mass transfer when a fluid is flowing past another immiscible fluid or it's flowing past a solid surface. So that's the requirement for convective mass transfer. Now, when a fluid is said to be in turbulent flow and is flowing past a surface, the actual velocity of small particles of fluid cannot be described clearly as laminar flow. So you have to understand that our previous discussions are all assumed that our fluid is behaving in laminar regime, or our flow is in laminar regime. Although there is one particular problem wherein in the case of agar, we have dipped it into a particular turbulent pure water solvent. In that case, though we have molecular diffusion, we had assumed that the small particles are behaving as in it is in laminar flow. Now, in real convective mass transfer, these particular small particles that are diffusing past another immiscible phase or that is coming from a solid surface to a non-diffusing flowing fluid, they are actually not in laminar flow. They are in turbulent flow. Now, if fluid is laminar, its flow is in the form of streamlines, and its behavior can be described by a pure mathematical expression. Now, however, if it's in turbulent flow, there are no streamlines, but rather the fluid flows randomly in chunks, or shall we call, or large eddies moving very rapidly. So when a solute dissolved from a solid surface or a solute from a particular fluid diffuses to another immiscible fluid, then the diffusion is turbulent. And eddy transfer is faster in comparison to a simple molecular transfer, just like diffusion. So in this case, there's a need for you to know what is the equation to use when we have this scenario, the convective mass transfer, and what appears in those particular equations. Now, speaking of equations, it is summarized here in the form of a table as to equations that will apply for gases. So we have this particular equation. This is a flux equation for equimolar counter diffusion. So you know already what is equimolar counter diffusion. Now, in the case of liquids, this will be our formula. So if you notice that in gases, we're using the convective mass transfer coefficient, which has the subscript C, convective mass transfer coefficient, or it could be K sub G, which is now being multiplied to partial pressures because we're talking about gases, or it could be K sub Y prime, which is being multiplied to mole fractions. So Y for gases, and it's being multiplied to the difference in the mole fractions at points 1 and point 2. This is also at points 1 and point 2, referring to partial pressures, and this is concentrations. Concentration of a gas, which is expressed in terms of, or could be expressed in terms of partial pressure divided by the product of RT. Okay, so this is K sub C prime, K sub G prime, and K sub Y prime. As to the relationship of these three, you can see it in here below. So how is K sub Y related to K sub Y prime? How is K sub G related to K sub Y and K sub Y prime? So all these formulas for the different forms of the convective mass transfer coefficients are related to this particular set of equations. Now this is for gases, equimolar counter diffusion. In liquids, we also have the same, but this time instead of using G as the subscript in here, we have already L for liquid, and in terms of using K sub Y prime, now we are using K sub X prime for liquids. And of course, since it's a liquid, we will not be using the Y for mole fractions, but rather we will be using the X for mole fraction representation. This first set of equation is for equimolar counter diffusion. We have a different set of equation for a solute A diffusing through a stagnant or non-diffusing B. This non-diffusing B could actually be non-stagnant, but as long as this B is not going to diffuse to the flowing A or to the solute A phase, which is going to diffuse to it. So only A is free to diffuse to B, but B should not be diffusing to A. If that is the case, if B is free to diffuse to A, to the phase containing A, then that would be now the case of counter diffusion. It will be equimolar if the amounts of moles diffusing past another in countercurrent direction are equal. So this is for gases and this is for liquids. And I have mentioned already that this will be your conversion for the mass transfer coefficients, the different mass transfer coefficients. If we have one for gases, just like in here, we also have a set of conversion for liquids. Now, here the density is the density of the liquid and M is the molecular weight. So, in the formula for liquid, so the density of the liquid and M is the molecular weight. Now, you have here the corresponding units for the K sub C, the K sub L, the K sub C prime, and the K sub L prime. So, these are the units. So, meter per second, this is your set of units for this one. And for the Kx, Ky, K sub X prime, and K sub Y prime, this will be our units. K sub G, K sub G prime, this will be our unit. So, these are this is actually the set of preferred units for these different mass transfer coefficients. So, in our problem later on, you will see that we need to convert from one form of the convective mass transfer coefficient to another. And if you notice, the corresponding formula is, or set of units rather, not formula, will be the same. Now, if you're going to mathematically analyze the units that are appearing in the formula, there is a typographical error in the unit for the K sub Y prime and the K sub X prime. The K sub Y prime and the K sub X prime does not have a per mole fraction unit in the denominator, or a per mole fraction unit. Only the K sub X and the K sub Y has the per mole fraction, but this two that has the prime does not have the mole fraction unit. Otherwise, the formulas will not agree. So again, for the K sub Y prime and the K sub X prime, the denominator is not, or should not contain, the mole fraction unit. Only the K sub X and the K sub Y. Now, for turbulent mass transfer, this is our flux equation. Generally, this is our flux equation, whether we're talking of a liquid or a gas, because if it's a gas, all you have to do is change these concentrations to partial pressure divided by the product of R and the absolute temperature. So, this could be viewed as our main flux equation for turbulent mass transfer. And this K sub C prime will be now the molar diffusivity of A to B plus, we call that epsilon sub m as the mass eddy diffusivity. The mass eddy diffusivity, which is in meters squared per second. And this S2 minus S1 is again the diffusion path, the length of the diffusion path. Now, since your mass eddy diffusivity here has a bar over it, then this should be viewed as the average mass eddy diffusivity of all molecules that is diffusing. Now, you could see also that you have in the formula in here the YBM, the XBM. So how do we determine this? Because in order for us to be able to convert from one form of the mass convective mass transfer coefficient to another, there's the occurrence of these particular expressions. So the formula to use in converting or in finding XBM and YBM, this is for a liquid and this is for a gas, is given here. Actually, it's just the log mean mole fraction difference. Okay, from points 1 and 0.2 of your B species, and this one also from points 1 and 0.2 of your B species. Okay, or the B species in here is the non-diffusing liquid in the second scenario, wherein you have A diffusing through a non-diffusing B. Okay, so this will be the formulas that we're going to use, and we're going to refer to this set of formulas later on as we encounter the scenario of convective mass transfer. So to apply the formula, so we have this sample problem here, and it talks about a large volume of pure gas B at 2 atm pressure is flowing over a surface from which pure A is vaporizing. Now, in this scenario, we should view that the pure gas B is flowing over a surface where pure A is vaporizing at this particular pressure. Not that pure gas B is at this particular temperature, but rather the scenario wherein A is vaporizing through the flowing gas B is all occurring at this particular temperature of 2 atm. Now, the liquid A completely wets the surface, which is in this case blotting paper. And hence, we can say that since A completely wets the surface, the partial pressure of A at the surface at the same time is also equivalent to the vapor pressure of A at the temperature of 298 Kelvin, which is 0.2 atm. So this is actually the pure vapor pressure of A, equivalent to the partial pressure of A at the surface. Now, the K sub Y prime has been estimated to be 6.78 times 10 raised to negative 5 kilomole per second per meter squared per mole fraction. So notice that this is in per mole fraction. But if you will substitute later on this set of units to a formula, this per mole fraction will not be working against the final unit set of units that is provided in the problem. So we will just take this out per mole fraction. So we will just have it 6.78 times 10 raised to negative 5 kilomole per second per meter squared. Now, the per mole fraction will only appear in the K sub Y without the prime. The same thing with the K sub X without the prime. Now, in here, we are after the vaporization rate of A, and that's the flux, the molar flux of A, and also the value of the two different forms, the two other forms of the convective mass transfer coefficient of A. So the problem gives us the K sub Y prime. So this same problem is also now asking for the K sub Y and the K sub G, so that we'll be able to utilize the set of formulas that were provided in the table. Okay, so for us to be able to do or find the solution to this problem, we need to go back again to our board. Okay, so if this is for this particular problem, we need to illustrate what's happening, actually happening in here. So I'd like to start from the given, that way we'll fully understand how the solution has to be started in the first place. So we will start with the given. So let's say, for example, I will draw this line, and this is where your flat surface, this is your flat surface, and this contains A, and this A is going to diffuse. So the direction of diffusion is perpendicular to the surface, but from the surface. And this is B. B is flowing past A. If we'll have the surface as point 1, and this entire region here, will the very large volume of B is flowing past through, is point 2, anywhere there. Then at 298 Kelvin and 2 atm, so this entire scenario is happening at 2 atm and 278 Kelvin. So this is the condition in which this thing happens. And it is stated also that since our flat surface is totally wetted by A, we can say that the partial pressure of A, so I'd like to place here 1 because this is our point 1, is equal to the pure vapor pressure of A at the indicated temperature of 200. By the way, this is 298 Kelvin, and it is equal to 0.2 atm. Now at this particular region wherein we have the bulk of fluid B passing through over the surface wherein A is diffusing from, we can say that in here the partial pressure of A is equal to 0, because in this region we only have B. Okay, we only have B. Now your convective mass transfer coefficient in the form of K sub y prime is 6.78 times 10 raised to negative 5. So kilomole per second per meter squared. I don't want to write anymore the per mole fraction because I like to write it on the K sub y. Now, this is the entire given information, and the problem requires us to determine the rate of vaporization. The rate of vaporization of A, and in that case, that's the flux. And we are to determine the other forms of the convective mass transfer coefficient. So in that case, that is the K sub y and the K sub g. Okay, so we will now go to the solution. So for our solution, of course, we will write the formula as practice, the formula that would lead us to the required information. So we have Na, which is equal to K sub y, Ya1 minus Ya2. Okay, where did this particular formula came from? This came from the table for a diffusing A through a non-diffusing B. So that's the second scenario in the table. For solute A, which is diffusing to a non-diffusing B or a stagnant B. In this case, our B is not stagnant because it's moving. Actually, it's moving over the surface where A is diffusing from. But it's non-diffusing. It will not diffuse counter-currently to the phase containing the A, or to your solid surface which is containing the A. So the scenario that applies here is the second one. A diffusing to A, non-diffusing B. So this is our formula. Okay, in this formula you have the K sub y. And we cannot find the k sub y for now, or it's not given in the problem, because in the problem what is provided is the k sub y prime. So we need to look for a formula that will give us the k sub y from the k sub y prime. And that particular formula, this one also came from the table, and that formula is k sub y bm, or the log mean mole fraction difference. Now, so if I want the k sub y, then that would be the given k sub y prime divided by the y bm. Okay, I'd like to place this as equation 1 because we can still solve for the flux, or the vaporization rate. Now, I need to determine y sub bm because it's not yet known here. I only know so far the k sub y prime. So this is our equation 2. So your y sub bm, being the log mean mole fraction difference, will be y b2 minus y b1 all over the ln of y b2 minus y b1. Now we need to determine then the y's, y b2 and y b1. So this is again equation 3. Now in the case of y b1, since we only have a component mixture, when the A has already diffused to B, then your y b1 is equal to 1 minus y a1. And this will be 1 minus, so your y a1 will be the partial pressure of A over the total pressure of the system of A and B. So in this case, this will be 1 minus 0.2 over 2. In this case, that will be 1 minus 0.1, and this is equal to 0.9. Now, in the case of YB2, I have another sheet for this. In the case of YB2, you will have 1 minus YA2. Now, 1 minus YA2, we need to determine the mole fraction of A, the diffusing A in B. So, if you're going to look at our illustration here, the mole fraction of A when it diffuses to B, which is very large in bulk, as stated in the problem, then here we can say that the mole fraction of A at this point is equal to 0. Why? Because this is a very large bulk phase consisting only of pure B. So we go back to this and then equation, and then we substitute YA2 being equal to 0. So this is equal to 1. Then from your equation here, which is equation 3, you can determine the log mean mole fraction difference of B. So your YBM will be equal to 1 minus, so in this case, you have 0.9 here. So you have minus 0.9. And you have 1 minus, or rather ln of 1 over 0.9. So your answer in here for YBM is equal to 0.95. So knowing YBM, now we're going backwards, we can go back to equation 2. So by the way, this is from 1. So from 2, knowing YBM, now we can determine the K sub Y, which is your K sub Y prime, or 6.78 times 10 raised to negative 5. And we divide that by your Y sub BM. This one. So this is divided by 0.95. Your value now for K sub Y will be 7.138 times 10 raised to negative 5. So since you have now, this one is mole fraction, this is mole fraction, so this does not have any unit. Actually, the unit here is mole fraction. So you can have this now as kilomole per second per meter squared per mole fraction. Okay. If we insisted that our K sub y prime, this one, the value that is given in the problem is per mole fraction, the resulting unit for the K sub y will be per mole fraction squared, because this 0.95 has a unit equal to mole fraction, because this 1 and this 0.9 is mole fraction, so the unit is mole fraction. So there must be some typo error in the book. So your ky, your K sub y now is equal to 7.138 times 10 raised to negative 5. So from, by the way, this one is equation 3, so this will be our equation 1. So we'll just change the number here. So this is from 3, and from equation 1 we will have the flux equal to ky, this ky, the 7.138 times 10 raised to negative 5, and we multiply it to ya1. So our ya1 is the 0.9, or rather 0.1. We'll see. Our ya1, so this is our ya1, it's 0.9, 0.1, because our 0.9 is ybm, so 0.1. So we'll change this one to 0.1. So this is 0.1, and your ya2 is, as I said, 0 in the given, because at point B we have pure, or at point 2 we have pure gas B, because it's very large, meaning the value of A diffusing to B will not matter as to the amount or the mole fraction of A in B, because B is very large as stated in the problem. So in here you will have now the Na, or that's the rate of vaporization, to be equal to numerically the same as the K sub y, but we will add to the exponent, or we will add one negative value to the exponent of negative 5. So this is now kilogram mole A, because A is the one that is diffusing, per second per meter squared. So notice that if your set of units for the K sub y is kilogram mole per second per meter squared per mole fraction, if you're going to multiply this with this mole fraction, this one is gone. And just like any molar diffusivity or flux, the set of units is always kilomole per square area, or per area per unit time. So this is correct. So this is our Na, and this is one of the requirements in the problem, the rate of vaporization of A. So as to the conversion, it's just a matter of formula as to finding the value of K sub. We are required for K sub y and K sub g. So in the case of K sub y, we already did determine that one, and the value is this. Okay, otherwise we can't find the rate of vaporization or the molar flux if we haven't determined in the first place the K sub y. So the last will be the determination of the K sub g. So your K sub g, based again on the table, the formula that will convert your K sub y prime to K sub g, or it could be K sub y to K sub g. So you have options actually. So in this case, I'm just showing to you based on what is the original given. This is how we convert from K sub y prime, the given, to K sub g. So that K sub y prime will be divided by Py sub Bm, and the rest will just be a matter of substitution. So the given in the problem for K sub y prime is 6.78 times 10 raised to negative 5. This in the problem has a unit of kilomole per meter squared per second. it has to have a mole fraction here. But let's say I will not write it down so that we could check later on if the set of units will agree. Your pressure is 2 atm. And this one is mole fraction. YBM has a unit of mole fraction. And we have determined that YBM already to be 0.95. So unit of mole fraction. Now, the resulting unit for K sub G with the value will be 3.568 times 10 raised to negative 5 kilomole per second per meter squared per atm. Okay? Let's see if in the table our set of units will be agreeing with this. So this will be kilogram mole per second per meter squared per mole fraction for K sub G. To check whether there's really a typo error in the set of units for K sub Y prime. So let's go to our table. So let's say I will write down here K sub G, and this is one of the unknown that we have determined already. So we have 3 unknowns, and we'll go back to our slide and check whether we have the unit that is to be followed. So for K sub G, we have kilogram mole per second per meter squared per atm or Pascal. So in our problem, so it does not have a mole fraction unit, and we have a mole fraction here. That's the contention that the given in the problem is per mole fraction here. So these 2 units cancelled out. So this does not have any set of units. But if we're going to go back to our previous equation, like this one, determining the K sub Y from the K sub Y prime and the YBM, this one has a unit of mole fraction. And if it's mole fraction here and this is per mole fraction, this will be mole fraction squared. So I'm not really sure why they placed that these 2 will just have the same unit. So we will just follow what the textbook gave us as to the set of units, because I'm wondering why these 2 have the same set of units, wherein based on the formula they should not have the same units, because this one, the log mean difference in the mole fraction of B will have a unit of mole fraction, because these 2 are mole fractions just like this. So mole fraction, this one is dimensionless. So this should have been mole fraction. If you have a per mole fraction here and a mole fraction here, the resulting unit of K sub Y should have been per mole fraction squared. But nonetheless, since the problem says that it should be the same, the set of units will be the same, then we will follow through. But I can't validate why they should have the same set of units based on the formulas provided. So we'll just stick on what is provided in the textbook, and that's it. The K sub Y and the K sub Y prime should have the same unit, even though in terms of the formula they should not have the same unit. As you can see here, if this is already per mole fraction, this should have been only kilomole per second per meter squared, because you have already here the mole fraction unit. This should have been kilomole per second per meter squared per mole fraction squared, so that when you multiply it with a mole fraction, your K sub Y prime will have a per mole fraction. But nonetheless, this is how they gave us. So this we will follow as to the set of units. So the K sub X, the K sub Y with the prime and without the prime has the same set of units. That way, the others here will have the set of units that they should have. Okay? So in this particular problem, I have shown to you how to make use of the of one particular flux equation, and that is in the second case here. And I've shown to you how we convert from one expression or form of the convective mass transfer coefficient to another. So as to what particular equation to a specific convective mass transfer problem are you to use, that would depend on only two scenarios here that's given. So it could be equimolar counter diffusion or diffusion of a solute to a non-diffusing medium or a flowing medium in this case, because we have convective mass transfer. Okay, so in our next discussion, we'll be discussing now the role of the shall I say the geometry of the flowing, the role of the geometry of the, shall say the equipment or the environment in which our flowing fluid is flowing into. So that would be the next thing that we're going to discuss.